Inside Airbus's plane manufacturing system, aviation is treated as a discipline of absolute precision. Nothing here is casual. Nothing is rushed, because every aircraft must perform flawlessly across continents, climates, and decades of service. The story begins before assembly ever starts. Airbus designs each aircraft as a complete digital organism. Engineers create full digital twins that simulate stress, vibration, pressure, temperature, and fatigue over tens of thousands of flight hours. Every structural decision is tested virtually long before physical components exist. When manufacturing begins, it follows this digital truth exactly. Fuselage sections arrive already shaped to near final form. These massive cylindrical structures look simple from the outside, but they are engineered with microscopic tolerances. Thousands of holes are drilled robotically, each one placed with extreme accuracy to ensure long-term structural integrity. Riveting is relentless and unforgiving. Automated systems install tens of thousands of fasteners, each logged and verified. These fasteners manage pressurization forces, aerodynamic stress, and vibration on every flight. One imperfect rivet is unacceptable. Human inspectors move continuously. They verify alignment, surface quality, and structural consistency. Machines provide repeatability. Humans provide accountability. Aviation demands both. Wing assembly defines Airbus's engineering philosophy. Modern Airbus wings are flexible structures designed to bend during flight. They are assembled on enormous jigs where laser systems verify alignment across vast distances. Composite materials and aluminum structures are layered carefully under controlled environmental conditions. Temperature and humidity are regulated, because materials behave differently depending on their environment. Precision here determines how the aircraft responds to turbulence years later. Once wings are complete, fuselage sections are joined. Nose, center, and tail sections are aligned and locked together. Laser systems verify straightness across the full length of the aircraft. Deviations are corrected immediately. There is no tolerance for cumulative error. Inside the aircraft, complexity multiplies. Kilometers of wiring harnesses are routed through the fuselage. Hydraulic systems, fuel lines, air conditioning ducts, and structural supports are installed layer by layer. Every system is color-coded, tested, and digitally recorded. Nothing is hidden. Everything is traceable. The cockpit is assembled like a command center. Flight computers, avionics racks, and control interfaces are installed with redundancy everywhere. No single failure is allowed to compromise safety. Systems are designed to fail gracefully, without pilots ever noticing. Landing gear arrives next. These assemblies must absorb enormous forces during takeoff and landing. They are tested repeatedly before installation, then tested again after. Brakes, tires, and retraction mechanisms are treated as flight-critical systems because they are. Engines arrive separately. Jet engines are among the most complex machines ever created. They are mounted under the wings with extreme care, connected to fuel, control, and monitoring systems. Every interface is verified both digitally and physically. At this stage, the aircraft looks complete. But in aviation, appearance means nothing, because an aircraft is not defined by how it looks in the factory, but by how it performs thousands of meters above the ground. That proof begins next. If you want to continue inside how Airbus tests, verifies, and certifies aircraft before they ever carry passengers, make sure to like the video. When an Airbus aircraft leaves the main assembly line, it is still not trusted. In aviation, nothing earns trust by existing. Trust is earned only through proof. Testing begins on the ground, and it is exhaustive. Every electrical system is powered on independently, then together. Engineers deliberately overload circuits, simulate failures, and verify redundancy. If one system shuts down, another must take over instantly without pilots needing to react. Hydraulic systems are pushed next. These systems move flight controls, landing gear, and brakes. They are pressurized and cycled thousands of times. Engineers monitor response times, pressure stability, and microscopic leaks. Any irregularity, no matter how small, is investigated. The cabin is tested as a life support environment. Pressurization systems simulate flight at cruising altitude. The fuselage flexes slightly under pressure, just as it will in the air. Temperature control, airflow, and oxygen systems are measured continuously. Passengers may never notice these systems, but their safety depends on them every second. Avionics testing is relentless. Flight computers run thousands of simulated flights without leaving the ground. Engineers inject weather failures, sensor conflicts, navigation errors, and pilot inputs. The aircraft must respond correctly every time. Landing gear testing is brutal. Gear is extended and retracted repeatedly. Brakes are tested under extreme loads. Tires are spun to take off speed and stopped abruptly. These systems must perform perfectly during the most violent moments of flight. Vibration testing follows. The entire aircraft is shaken deliberately. Engineers measure how the structure responds to stress frequencies that occur during turbulence, engine resonance, and landing impacts. Unexpected vibration patterns are analyzed and corrected. Once ground testing is complete, flight testing begins. Test pilots take the aircraft into the sky under controlled conditions. These are not routine flights. Each flight is a carefully planned experiment. Every maneuver is intentional. Every response is measured. Handling, climb performance, stability, and automation behavior are evaluated. Autopilot systems are engaged and disengaged repeatedly. Control surfaces are tested across the full flight envelope. The cabin is monitored in flight. Noise levels, vibration, and environmental stability are measured while airborne. Airbus is not only testing safety, but predictability and comfort over long hours in the air. After landing, inspection resumes immediately. Engineers download flight data, inspect structures, and review system behavior. Software is refined. Procedures are updated. The aircraft flies again. This cycle repeats. Because in aviation, one successful test proves nothing. Consistency proves everything. Only after passing every required ground and flight test does the aircraft move forward. But even then, Airbus's responsibility does not end. Because aircraft do not operate in laboratories. If you want to see how Airbus continues supporting aircraft long after delivery, and how real-world data shapes future designs, make sure to subscribe to the channel. When an Airbus aircraft is delivered, manufacturing does not end. It expands into service. Before handover, airline representatives walk the aircraft line by line. Cabin layouts, avionics options, operational requirements, and documentation are verified in detail. Acceptance flights confirm that the aircraft performs exactly as promised. Delivery is precise, not ceremonial. Once accepted, the aircraft departs under its own power, already trusted to operate in one of the most demanding environments on Earth. Then the real world begins. Commercial service introduces variables no test program can fully reproduce. Weather systems, airport infrastructure, flight schedules, pilot techniques, and passenger loads interact constantly. Airbus designs aircraft to handle this complexity and to report on it. Every flight generates data. Sensors across the airframe, engines, and systems monitor performance, loads, temperatures, and behavior. This information flows back to airlines and to Airbus engineering teams in near real time. Patterns emerge. Anomalies are investigated. Improvements are identified. This feedback loop is continuous. If a component shows unexpected wear, maintenance guidance is updated. If software behavior can be improved, updates are issued. If operational data suggests design refinements, future aircraft evolve. The factory learns from the sky. Engineering teams analyze fleet-wide data to refine materials, systems, and manufacturing processes. Lessons from thousands of aircraft in service feed directly into new designs and production improvements. Support never stops. Airbus provides training, engineering assistance, and digital tools that allow maintenance teams to trace every component back to its origin. Predictive maintenance reduces downtime. Reliability improves across the fleet. Safety is cumulative. Every lesson learned increases confidence, not just for one aircraft, but for all aircraft that follow. Aviation advances through discipline, repetition, and continuous learning. Inside the factories, production continues but smarter. Digital twins evolve. Assembly methods improve. Testing becomes more efficient without becoming less rigorous. New aircraft benefit from decades of operational experience embedded into every decision. This is why aviation moves carefully, because trust cannot be rushed. Airbus's plane manufacturing system is not just about building aircraft. It is about ensuring that millions of people can cross oceans every day without thinking about the engineering beneath them. That invisibility is the ultimate achievement. Which part of Airbus's aircraft journey impressed you most? The precision assembly, the relentless testing, or the continuous learning after delivery? Leave a comment and share your thoughts.
Generators.
On.
Engine start switches.
Flight idle. Engaging.
Look at the altitude metrics here. That's a clear improvement.
Yes, the adjustments worked perfectly.
Check the telemetry readings on the auxiliary screen. They are fluctuating rapidly.
Rerouting the data stream now. Stand by.
Zooming in on the transient data now. See the phase alignment here?
Yes, that correlates with the input parameters. It looks stable.
Check the oxygen levels now. They are dropping fast.
Wait, it's stabilizing. We are in the green.
Check the alignment on row 32. The sensor reading is slightly off.
I see it. The latch mechanism needs adjustment before final sign-off.
The upholstery is fine.
The latency on the sliders is negligible, and the haptic response confirms the input immediately. The ergonomic placement is superb.